In this episode, I'll show you what potato starch looks like under polarized light. I'll also conduct an interesting experiment, breaking down starch granules using amylase from saliva. Additionally, we'll explore how starch appears in different plants, such as rice, tapioca, and banana. I'll also answer the question, why does bread taste sweeter the longer we chew it? Let's start by examining potato starch under a microscope with polarized light. To do this, we need two components, a polarizer and an analyzer. I'm using a ready-made set designed for my microscope, but you can also use polarizing film, which you can find in 3D glasses. The important thing is that the polarizer should be placed under the specimen, near the light source, while the analyzer goes above it. As we start rotating the polarizer, we'll notice that the background gradually darkens. At this point, the starch granules become particularly fascinating. We can see how their structure forms characteristic dark and bright zones, creating regular bands or rings around the center of the granule. This intriguing effect results from the ordered structure of starch and its optical properties. Now, let's try breaking down starch using amylase. I placed some potato starch on a microscope slide and added a few drops of water. Then, I covered the sample with a cover slip and placed it under the microscope. In a separate container, I had saliva, which I introduced under the cover slip using a pipette. However, under the microscope, there were no visible signs of starch breaking down. But what happens if we dissolve starch in water and heat it? At room temperature, starch exists as granules, where amylose and amylopectin are tightly packed in an orderly structure. When heated, the granules absorb water, swell, and their structure breaks down. Amylose and amylopectin lose their order and mix freely with water, forming a sticky, thick mass. The simplest examples of this process can be found in the kitchen. This is how pudding or thickened soups are made. I mixed some of this starch gel with water, placed it on a microscope slide, and observed it under the microscope. The starch granules appeared distorted, larger and flatter. After heating, they also had low contrast, making them difficult to see clearly. I then added amylase to the sample, using my own saliva. I placed a drop on one side of the cover slip and a piece of paper towel on the other side to help draw the enzyme under the cover slip. Under the microscope, we could see the starch granules slowly breaking down into maltose. And now, why does bread taste sweeter the longer we chew it? Bread becomes sweeter because, during chewing, the amylase in saliva breaks down starch into simpler sugars like maltose, giving the bread a progressively sweeter taste. Now let's move on to the next stage, which brought quite a few surprises, observing starch from different plants under the microscope. Starch granules can vary in shape, size, and structure depending on the plant species or even different parts of the same plant. Based on the number of centers and amyloplasts, starch granules are classified as simple, with a single center, or compound, with multiple centers. Let's start with potato starch. Its granules are large, oval, and quite regular in shape. At 400 times magnification, we can clearly see their layered structure. Thanks to their size and easy availability, potato starch granules are ideal for microscopic observation. Next, let's take a look at rice starch. On the right side of the screen, I've included an image of potato starch for comparison. Compared to potato starch, rice starch granules are much smaller, and some form compound granules made up of many tiny elements. Aside from its culinary uses, rice, especially rice water, has a long history of use in Asia. Over 1,000 years ago, Japanese court women discovered its remarkable effects on the skin. It helps reduce sebum production, tightens pores, mattifies, and gently brightens the skin. Another example is cornstarch. Its granules are single, very small, and irregular in shape. Tapioca starch is also very fine. It's derived from cassava and has many applications. In cooking, it works well as a thickener for sauces and soups. In cosmetics, it's valued for its absorbent properties and silky texture, making it a great alternative to talc. It can be found in powders, lotions, and other skincare products, where it helps absorb excess oil. Finally, let's look at banana starch, which I'll stain with iodine. Depending on how much iodine is absorbed, the granules change color, from light blue to purple to almost black. This process happens within seconds. First, a light blue shade appears, which gradually darkens. However, over time, the color begins to fade, so keep this in mind if you want to preserve the sample for a longer time. If you enjoyed this episode and want more content like this, subscribe to the channel and let me know in the comments what you'd like to see under the microscope next.